In this video, we'll discuss a few properties of elements. From atomic point of view, current depends on the movement of relatively loosely bound electrons, which can be removed from their atom by the applied potential difference. We have seen earlier that elements with s electrons are least bound, and thus such elements are expected to have small resistivities or higher conductivity. We know that resistivity is connected to is equal to 1 over conductivity. Now let's look at magnetic susceptibility. When a material is placed in a magnetic field B, the material becomes magnetized and it acquires a magnetization which we represent by M. That's why this magnetization is proportional to applied magnetic field. So mu naught M is equal to chi B, and here this is the magnetic susceptibility. So now depending on the values of this chi value or magnetic susceptibility value, we can further categorize such materials to be either paramagnetic, diamagnetic, and so on. Now if the magnetic susceptibility is greater than 0, then it's called paramagnetic, and if it's less than 0, which is negative, then it's diamagnetic. And material that remain permanently magnetized even when magnetic field is removed are known as ferromagnetic materials, in which this magnetic susceptibility is undefined. Now let's look at how the graph will look like for paramagnetic, diamagnetic, and ferromagnetic materials. If we plot M versus B, or applied magnetic field, then for a paramagnetic material, the graph will look like something like this. So this is for a paramagnetic material. And for a diamagnetic material, the graph will somehow look like this. So this is for diamagnetic material. However, for ferromagnetic material, the M versus B curve looks very different. So if we plot a graph for ferromagnetic material, first the magnetization value increases and it reaches a saturation, and even when magnetic field is removed, magnetization does not go back to 0 and it retains a magnetization. And if you now apply magnetic field in opposite direction, similar behavior is observed, and when magnetic field is removed, it does not go back to 0. And so in this kind of ferromagnetic material, you get this kind of hysteresis loop, we call it. Now from atomic point of view, magnetism depends on L vector and S vector of the electrons in an unfilled subshell. Now let's look at S subshell elements. It can be an element could belong to alkali elements, or it could belong to alkaline earth elements. In alkali, they have NS1 format of electrons at the end, and alkaline earth material have NS2 sort of distribution of elements electron at the end. So all these NS1 alkali elements are very reactive, because this one electron in S subshell can easily be removed. However, NS2 is, even though it's fully filled, it is also reactive, but not as reactive as alkali elements. One of the example of P subshell elements is halogens, which have configuration of NP5, and the examples can be fluorine, chlorine, bromide, iodide, and so on. So they have P orbital can take 6 electrons, but if you notice, it has one lack of electron. Just remember that a filled p or subshell is very stable configuration. If p subshell is slightly unfilled, that element will readily form compounds with other atoms that can provide an extra electron to actually complete the p subshell. And one example can be, so for example, these halogens have slightly unfilled p orbital. So if we know that sodium can give one electron to easily to chlorine, and so what happens is Na plus and Cl minus can just become NaCl. So what happened, this extra electron of Na goes into the p or subshell of chlorine to make it completely full. So that way it makes a compound. P subshell series is diamagnetic with a characteristic negative magnetic susceptibility. Now let's look at transition metals, which is basically 3 rows in which D subshell is filling. That is scandium to zinc, yttrium to cadmium, and lutetium to mercury. Important to note that is H subshell or electrons in these have larger n than the D electrons, and that's because if you remember when we gave the energy levels of various N and L, we saw that in some cases, for example 3D is filled later on, and 4s subshell is filled first. If you look figure 8.9 in the textbook, you will see that there is a sharp rise at the center of the sequence when you plot the resistivity, and there is a sharp drop near the end, and that sharp drop at the end indicates small resistivity for copper, silver, and gold. We all know that copper is small resistivity or highly conductive material, and that's why we use copper in all the electrical lines around us. So if we look at the electronic distribution, so at the end copper has 4s2 3d9 configuration, but we know that a filled D subshell is more stable than S subshell. Thus we get copper will show this kind of electronic distribution, and we see that there is only one electron in S subshell, which is relatively free and easy to take out. So relatively free single S electron makes copper highly conducting or less resistive. Similarly, for silver and gold, we have for silver we have 5s1 4d10 configuration, and for gold it's 6s1 and 5d10 configuration. And just like copper, silver and gold are also less resistive, but we don't use them in wiring because these are much more expensive as compared to copper. So we have seen that filled D subshell is very stable, but we also, there's another thing, even the half filled D subshell is also very stable, and examples could be manganese with 3d5 configuration. And if an element is stable, what does that mean? It will have larger resistivity. That means electron cannot be easily removed. So these elements with half-filled d orbitals are also very stable, and that's why they have larger resistivities or smaller conductivities. An electron cannot be easily taken out. Also note down that transition metals have paramagnetic susceptibilities. That means this susceptibility value is greater than 0. Now let's look at another set of elements which are called lanthanides. These are also called rare earth elements. Total in all there are 14 rare earth elements, all the way from lanthanum to ytterbium. And in this series of lanthanides, 4f subshell is being filled after 6s subshell. And because of larger orbital angular momentum of f subshell electrons and also larger number of f shell electrons that can align their spin magnetic moments, the paramagnetic susceptibility of the rare earths are even larger than those of transition metals. One thing I forgot to mention earlier, that the transition metals, there are d orbitals that are filled, and these d orbitals in transition metals are also responsible for the ferromagnetism. Just reminding you that right now I'm talking about transition metals and not lanthanides. In lanthanides, 4f subshell is being filled, and in transition metals it is electrons, d electrons. So for iron, which has a Z number of 26, nickel is 27, and cobalt has 3d8 configuration at the end, whereas nickel has 3d7 configuration at the end, and iron has 3d6 configuration at the end. And let's look at for iron with 3d6 configuration. You know how you start filling up electrons. So you first fill up electrons without pairing them, and the 6th electron will go as a pair. So we see that 5 electrons have parallel spins, therefore each iron atom has a large moment. But as soon as this d subshell is filled, the orbital and spin magnetic moments no longer contribute to the magnetic properties, and that is why copper and zinc in transition metals are diamagnetic. Because the d subshell is filled. Now let's look at inner electrons. You also remember Frank Hertz's experiment. If you don't remember, please take a look at it. When we pass accelerated electron beam of electrons through a chamber filled with mercury vapor, then we get this kind of current versus voltage graph. And such transition of outer electrons of an atom usually involves only a few electron volt energy. And these are associated with photons whose wavelength lie in or near visible part of electromagnetic spectrum. Inner electrons of heavier elements. Heavier means they have much more higher value of atomic number and atomic mass. So inner electrons of heavier elements are quite different because those are not well shielded and are very tightly bound. Therefore, when acceleration voltages in the range of 10 to the power 5 is applied, electrons from even the inner shells can be removed. If you remember Frank Hertz's experiment, in this one electrons from outer shells were removed and the voltages applied were like a 10 or 20 or 30 electron volt. Here 10 or 20 or 30 volt. However, the voltages you are talking about here is 10 to the power 5. So higher voltage you apply, higher energy it has to remove electrons from inner shell. So how much of energy is needed? If you look at example of sodium with with 11 atomic number, you see that in order to remove electron from 3s subshell, which is the outermost subshell, only 5.13 electron volt is needed. However, in order to remove electron from 2p subshell, 31 electron volt is needed. And further, to remove electron from 2s, which is further inner shell, 63 electron volt is needed. And which one is the innermost? It is 1s subshell. So in order to remove electron from 1s, you need 1041 electron volt of energy. So you see that as we go to inner electron, the energy requirement increases, right? And in this case, even 1041 electron volt energy is needed to remove electron from 1s orbital. Now, transitions that involve such inner electrons in an atom give rise to X-ray line spectra because of the high proton energies involved. We know that we need higher and higher energy to remove electrons from the inner subshells, and that is why such transitions that involve inner electrons give rise to X-rays, and X-rays have much higher photon energies. And if you look at X-rays are called by definition those electromagnetic waves which have 0.01 to 10 nanometer of wavelengths, and equivalent energies are from 100 electron volt to 100 kilo electron volt of energy. So here X-rays are emitted in transitions between more tightly bound inner electron energy levels of an atom. Now, under normal conditions, when you are filling up electrons, what do? You first fill up the inner shells and then go to the upper or outer shells, right? So under normal conditions, all inner shells are filled, and that's why X-ray transitions do not occur. Transitions means you have to have electron missing from there so that electrons from higher shell can go into the inner shell and can emit X-ray line spectra, right? So you have to remove first these inner shell electrons in order to observe such X-ray line spectra. So as I told you, we need to first remove an inner electron or inner electrons. Then an electron from higher subshell will rapidly make a transition to this inner subshell to fill that vacancy, and thus emitting X-ray photons. Okay. For example, if the vacancy is in K shell, K is the n equals to 1 shell. So we know that as the number of principal quantum number goes higher and higher, energy levels is increasing. So first is a K shell, then it's a L shell, and then M, N shell, and so on. So when 1s electron is removed, which was here, okay, in n equals to 1 shell, and when this one is removed, then electron from L, M, and N can make the transition. So if transition can be this, transition can be this one, or can be from n equals to 3 to n equals to 1, or can be from n equals to 2 to n equals to 1. Right? So with this, because the ultimately transition is taking place from higher levels to K shell. That is why such transitions lead to the wavelength series of line spectra, which are called K series. And if the transition is taking place from n equals to 2 to n equals to 1, it's called K alpha. If transition is taking place from n equals to 3 to n equals to 1, it's called K beta. And from 4 to 1, it's called K gamma, and so on. So important is these together, they are called as K series. So these together are called K series. Similarly, you can imagine if an electron is removed from n equals to 2 subshell, then transitions can take place from higher shells to n equal to 2 shell. It can be from n equals to 5 to n equals to 2, can be from n equals to 4 to n equals to 2, or n equals to 3 to n equals to 2. And so the wavelengths or the radiations emitted from such transitions are called L series. In similar manner, you get M series, N series, and so on. Let's look at an example for silver. If you look at the characteristic X-ray spectrum for silver, then you will see that you get actually some sort of series wavelengths which are called K series, and then you also get L series, and at higher wavelengths you get M series also. So along with this K, L and M series, you also see that silver shows this kind of continuous distribution as well, and this continuous distribution is a Bremsstrahlung spectrum. Okay, so over Bremsstrahlung spectrum you have K, L, M, N X-ray line spectra. In chapter 3, we discussed this continuous X-ray spectrum emitted by accelerated electrons. Here we are concerned with the discrete X-ray line spectrum emitted by atoms. Now it's easy to find an approximate relationship between the frequency of the K alpha X-ray line of an element and its atomic number Z. For example, a K alpha photon is emitted when L electron, which is n equals to 2, goes to a vacant site, vacant K shell, and when it goes to K shell, it is actually K alpha line, right? From L to K, then it's called K alpha line. When an electron in the L shell is normally screened by the two 1s electron, it sees an effective nuclear charge of Z minus 2. And when one of those 1s electron is removed, creating a vacancy, then for L shell electrons, Z effective will be Z equals to 1, Z minus 1. So if one electron is removed, so if this electron in K shell is removed, then for L shell electron, Z effective will be Z minus this 1 electron. Therefore, K alpha X-ray line can be analyzed as transition from n equals to 2 to n equals to 1 level in a 1 electron atom with Z effective equals to Z minus 1. Therefore, using equation 6.38, we can find out how much is the change in energy when such a transition takes place. So E2 minus E1 equals to minus 13.6. Here Z effective is Z minus 1 square. 1 over 2 square minus 1 over 1 square, and 2 is initial n and 1 is final n, and this value of delta E comes out to be 10.2 electron volt times Z minus 1 square. So this is a very important equation, that change in energy for this is equal to this formula. So in 1913 to 1915, young British physicist Moseley confirmed this equation by measuring the K alpha frequencies of most of the then known elements using diffraction method. Because this equation actually can be applied to any element with any z value. So he calculated for different elements, and for example, he also found gaps in his data, and which corresponded to a couple of z values for which elements were not known. For example, 43, 61, 72, 75, these were missing. And he also suggested that the existence of unknown elements that were later discovered. Now let's go to a different topic, which is actually a very important topic. It's about addition of angular momentum. So if there is only one outer electron, as in case of sodium, so this 3s1 electron has, let's say, quantum numbers n, l, ml and ms, then the entire atom behaves as if it had only those quantum numbers. So it's very important. Okay, so outer electron play an important role. So what if like sodium had only one electron in the outermost? What if the number of electrons is much more? Let's look at the example of carbon, for which Z equals to 6. So the distribution is 1s2, 2s2, 2p2. So it's no longer one electron in the outermost shell. So there are two electrons. Right? So what we do about this? How does the entire atom behave? Okay. So in order to find the angular momentum of carbon, we must combine the angular momenta of the two electrons, 2p electrons, to find the total orbital angular quantum number L, and also total magnetic quantum number ml. So we need to get total orbital angular quantum number and also total magnetic quantum number ml. So what if there are more than two electrons? So first couple the angular momentum of two electrons to give maximum and minimum value of L, and then couple each allowed L to angular momentum of the third electron to find the largest maxima, smallest minima. So let's look at example first for carbon, which is 2 electrons. So for carbon, the outer electrons are in 2p subshell, and there are only 2 electrons. So if we start to fill in, how will you fill in? You go first electron and then second electron goes here. So by the way, this box thing, how to fill up, we have seen earlier. So for the first box, ml value is +1, for second box ml value is 0, and for the third box ml value is -1. Okay, so angular momentum for the first electron is 1, and for the second electron it is also 1, because both are in 2p level. Okay, so here L maximum will be given as L1 plus L2, and when you combine it, the value is 2. And L minimum is given by magnitude of L1 minus L2, and if you look at this, comes out to be 0. Therefore, total angular momentum is either 0, 1 or 2. And this is because the possible values of L goes from L minimum to L maximum, and for two electron system, L maxima and L minima are given here. Now similarly, if you want to find out spin, then total S will be, let's start. So S maxima will be S1 plus S2, which is, they have spin of half, right? So half plus half equals to 1, and S minimum will be half minus half, and which is 0. So similarly, S will be 0 or 1. Okay, so we got this and we got this value. But for the ground state, will be identified by only one particular choice of L and S. But now we have 3 choices for L and 2 choices for S. So question is, which one would represent a ground state? Before I go further, let me revise once again. If you have 2 electrons in the outermost shell, then in terms of magnetic quantum number, ML value can be ML1 plus ML2. So total permitted values of ML are from minus L to plus L. So it can go from minus L to minus L plus 1 and so on. It will also have somewhere 0 and then L minus 1 to L. Now what happens for spin? For spin, the rules will be identical. That is, total S vector will be vector sum of individual spin. So for 2 electrons, each of which has spin equal to 1/2, total S can be either 0 or 1. An important point here to note is all the filled subshells have L equals to 0 and S equals to 0. That is the total angular moment, magnetic quantum number and spin moment. So we don't need to consider the filled subshells to analyze the angular momentum of an atom. Therefore, filled subshells do not contribute to the magnetic properties of an atom. Only the unfilled or partially filled subshells contribute to the magnetic properties. So remember, 2 slides ago we just asked what out of different possible combinations of S and L, which one would be the ground state. So Hund's rule will help us to find the ground state. So we reached 2 points. So very first point is, first find the maximum value for total spin magnetic quantum number ms using Pauli principle, and then that value of maximum value of ms will be your S. Then for that ms value, find the maximum value of ml consistent with Pauli principle. In that case, L is equal to maximum value of ml. Okay, so we saw the rule. Now let's apply it for the case of carbon, like we saw earlier. So we first find the ms max value, and that is 1. We saw that earlier, and that is why S is equal to 1. Now for 2p2 state, you have only 2 electrons, and these electrons go in Ml equals to +1 and Ml equals to 0 state. So the first electron will go to Ml max equals to +1, right? Now the second electron cannot go to the same Ml state because according to Hund's rule and Pauli's exclusion principle, well, according to Hund's rule, we first fill the electrons without pairing them. So second electron will not have Ml max equals to 1, but it will have Ml max equals to 0. Therefore, capital Ml max for the 2 electrons will be simply 1 plus 0 equals to 1. And when Ml value is 1, that is L equals to 1 state. So L equals to 1 and S equals to 1 is the ground state of carbon. Now let's quickly look at such state, ground state for nitrogen, and for nitrogen Z equals to 7, right? So distribution is 1s2, 2s2, 2p, 3. Now instead of 2 electrons, you have 3 outer electrons. So question is, what is the ground state of such an atom? So 3 electron will be filled like this, all 3 unpaired electron with Ml values of +1, 0 and -1. These are Ml values. Okay. So capital Ml value will be 1, 0, -1, which is 0. And that is your L value. And again, now look at these 3 electrons. Okay, all 3 will have Ms equals to +½ spin. So Ms max value would be ½ plus ½ plus ½, which is 3/2 S. Okay, so L equals to 0 and S equals to 3/2 is the ground state for nitrogen. Now I want you to look at similar cases for oxygen and so on. So I want you to do problem for oxygen, for which it is 2p4, so there are total of 4 electrons, and find out the ground state for oxygen atom with Z equals to 8. I will finish this in the class, so please go through all these examples, and I'll finish this. I'll show you the case of oxygen in the class.